Hi, this is CrossDot and Nabla, and today in this video we're going to be going over section 12.3, limits and continuity for real valued functions with multiple variables. And before we start off with going for multiple variables for limits, let's start off with what we know from single variable calculus and solving for limits, right? The definition for continuity, as we remember, is the limit as some value x is approaching c has to equal f of c, which means that it's defined at a point c, the limit exists there, and these are necessarily equal to each other, right? Three examples of where this doesn't work are you have your hole, you have your vertical jump, and you have a asymptote, right? So like for example, if this white line right here were to represent a function and we want to take the function, let's say f of x, the limit as x approaches 0 of f of x, this is going to go to negative infinity, but you have something else right here, it's going to equal dne, because these two sides aren't going to agree with each other. Also, f of 0 isn't defined, therefore we can't say that the limit exists at 0. And for limits in multiple variables, it's this similar idea, getting very, very close to some point f of x, y, right? Some point x, y in 3D space. The limit gets very close to it. It can actually approximate the value, right? We could only approach it from two sides in single variable calculus, but now we can approach it from any side we want, because we have more variables, we have more opportunities to manipulate these equations, right? And we'll get into that later on. And we have the definition of the limit. This is like the technical epsilon delta proof definition. We will not be going over this idea in this section. It's quite tedious, and it's not really the most, it doesn't really give us the most explanatory value for everything, so I don't think it's that valuable, but still cool to know. And before I even jump in to solving any of these problems, there are 4 main strategies that you will be using to solve these limits, right? The first one, we obviously remember this from Calc 1, direct substitution. Number 2 is algebraic manipulation. Number 3 is test paths. Like I mentioned earlier, there's an infinitely many paths you can take. Like for example, this right here, in 3D space, this has infinitely many paths it can reach. As long as it goes through that point A, comma B, it is a valid solution, right? And then fourth, we have polars, and this will come in useful with stuff like this. Whenever you see any of these types of equations show up, x squared plus y squared equals r squared is a really common one that you can use polars for substitution. And yeah, let's jump right into it. Example 1 is probably the most straightforward example you will see throughout any video in any video in our series. Just plugging and chugging. So it's gonna be just a lot of boring math. 3 is our answer. For 2, let's just try direct substitution. So just plug in 1 plus 0. 1 over 1 equals 1. It's pretty nice. And for example 3, this one's a little bit more tricky. So if you want to try this on your own, feel free to pause the video. Let's get right into it. Immediately what I'm seeing is, I'm gonna just try a direct substitution of the values. We get tan of 0 over 0. This gets me 0 over 0. I don't like that. What could I do to make this easier on me? Well, I see we have the x squared plus y squared components here. We could do this trick where this is going to be d and e. We could say that u equals x squared plus y squared, and the limit as this approaches 0, this is just going to approach 0. So I think we can just replace that in its entirety, and then we can do limit as u approaches 0, because that's ultimately what it is, right? 0 squared plus 0 squared is 0, yeah. Tangent of u over u. This gets me 0 over 0 again. But since we're in single variable now, and a single variable function, we can just use L'Hopital's rule. So we take the derivative of the top, which is secant squared u, derivative of the bottom, which is 1. The limit as u approaches 0, 1 over 1 is 1. That's kind of like a cool trick you can use. You could also use polars, but it'd be kind of tedious because you still have to do like L'Hopital's rule. And finding like these like cool substitution tricks is pretty nice. Yeah. Right here, example 4, this is going to be involving the limits of multiple paths. And I'll walk through this one real quick. So usually for these problems, if you have to hold one of these constant. So like, for example, if it's solving for this limit not existing, we have to make sure that the limits from limit, if we're saying the limit as x approaches 0, we're holding y constant, right? So it's going to be holding y constant, so it'd be 0 times x plus 0 cubed x squared plus 0 squared, 0 over x squared, limit as x approaches 0. This is going to go to be d and e, right? And we technically have our answer already, but we just want to show you for the sake of this video the other part of this problem. The limit as y approaches 0. Now we said that x is equal to 0. We hold x constant instead of y, holding y constant, because then we can just look at the different paths and see how it would look. So we hold x constant, so it would be 0 times y plus y cubed all over 0 squared plus y squared. This goes away, this goes away. So it's the limit as y approaches 0 of y cubed over y squared. And then the limit is y approaches 0, so it's going to be 0. These two do not match. Therefore, we know that this limit does not exist. For example 5, we're now going to use polar coordinates to solve this limit right here. If you want to try this on your own, given the polar identities we know, feel free to pause the video. Let's get right into it. So just immediately substitute everything in. And one common thing you will see is if we're saying that r squared equals x squared plus y squared, and we're going towards the origin, just plug it in directly for our radius. So we get 0 squared plus 0 squared equals r squared. So it means that we know that r is 0 for our limit. And now we're in a single variable instead of multiple variables, right? We have this, and then we have this going away. Then we have the limit as r approaches 0 of r cosine cubed theta. And regardless of what cosine theta is, it's always going to oscillate between -1 and 1. It doesn't really matter. We're looking as, this is technically a constant with respect to r, so we could actually just move this out front like that. and then have the limit as r approaches 0. This goes to 0, so therefore the entire thing goes to 0. B is the same idea. If you want to try this again on your own, feel free to pause the video. Just go right into it. Cosine theta over r. So just pull out the cosine theta. Cosine theta limit as r approaches 0 of 1 over r. This is going to be dne because it's going to be 1 over 0. That's not defined in math, so we can't say that has a value. And then finally for part C, we have this limit. And again, we're just going through all the variations of x squared, and x cubed, but that's all good for me. So we're going to have r squared cosine squared theta over r squared in its totality. The limit as r approaches 0. These cancel. And then we are left with limit as r approaches 0 cosine squared theta. We don't have an r here, but we have this, and this can vary regardless of the direction that we're going towards, right? So like if we have like a circle like this, it could be any theta on this interval, and it can give us any value from 0 to 1. And that's not really helpful for us, so we can just say that this limit does not exist because cosine theta varies along infinite paths, right? And one last thing for this section is going over continuity for multivariable functions. Like we mentioned at the beginning, if the limit is defined and the actual value is defined at a specific point, then the limit exists and that function is continuous at that point. And these rules still apply here, right? Like for example, right here, this point exists in space, in 2D space, just extend it up into 3D. And for this right here, this isn't defined in space because there is no point AB that corresponds with this, right? And the composition of functions is just referring to the same thing like before in single variable calculus, right? So if it was like f of g of x, right? That same idea, just scaled up into 3 variables. And yeah, for example 6, we have to show that f of xy is continuous for this function everywhere. And this one isn't that bad. So it's a compositive function, so it's like f of g of x. So if we know that sine is always continuous. This is always continuous. For any x comma y, and then therefore, there's also the therefore symbol, therefore f of xy is continuous everywhere. Example 7, determine where f of xy equals ln of 1 minus x squared minus y squared is continuous. So feel free to pause the video, try this one on your own, and let's get right into it. So for natural log, it has to be greater than 0, right? There's no absolute value, it's just a parentheses, so we know that this has to be greater than 0. So we can say that 1 minus x squared minus y squared is greater than or equal to 0. We move the x squared plus y squared to the other side. We flip, and then, and then we get this. So then we can flip this over like this. X squared plus y squared is less than or equal to 1. Oops. And then we can get our level, we can go back to like a level curve, honestly, and just draw out this poorly made circle, but you get the idea. And we can shape this all in because anything within the interior is fair game, but not along the edge. And I probably should have mentioned that beforehand. Whew. Yeah, because ln of 0 isn't defined, even though it's technically, even though you can say that's negative infinity, right? Because, you know, ln of 0 equals some x e b negative infinity, right? Technically, mathematically, we don't have a value for that either, so be a little bit wary of that, and I'll just draw these green dots around it to clarify that. Yeah. Example 8 is f of xy for this piecewise function continuous everywhere. Let's look at it. So if xy equals 0, then it would be 1. Well, what do we know about sine? What do we know about the values for sine of xy over xy? It would be that anything of like sine of a over a equals 1, the limit as a approaches 0, right? And for example, x comma y as it approaches 0, that's going to be a case where that's going to equal a, right? So anytime the value is going to be 0 for x or y, if we're doing the multiple paths, right? So like we can say that, like, for example, limit as x approaches 0, given y equals 0, we can say that sine of 0 over x, this is just going to become sine of 0 over 0, which is just 1. Same thing with the limit as y approaches 0, given x equals 0, sine of 0 over y, sine of 0 over 0 equals 1. And that gives us the same idea, right? So even if it's 0, 0 for both of them, it's still going to be sine of 0 over 0, which we know from calculus 1. That's like one of the most famous limits, that it's going to equal 0. It's going to equal 1, excuse me, because it means sine of 0 over 0. You can use L'Hopital's rule, you can use like the squeeze theorem, you can use any of those rules to solve for that. And that is pretty much it for this section. Thank you so much for watching, and I hope you guys have a fantastic day.